Hello and welcome. Today we're going to be talking about the natural numbers. And really what we're going to be doing is actually building the natural numbers. And we're going to start this building of the natural numbers from axioms and go all the way up to counting. And what I mean by that is that, we're not going to cover algebra yet. That'll be the next video. Okay, so we're going to talk about the axioms from counting. And again, this is what we're doing here is we're starting our real analysis by building the numbers from scratch. All right, so we're building numbers. From scratch. Okay, and what we mean by that, what we mean is starting with axioms. A set of axioms. Okay, so what's an axiom? An axiom is, I'll just give you the dictionary definition. It's sort of basically a set of premises, or a premise. A premise, or something that's self-evident. It's a fact that's self-evident, or taken without proof. I should say, assumed without proof. And it may be that there is not a proof, or it's basically a starting fact, and that's basically the other way of saying it, is it's a starting point. A starting point of reasoning. Okay, it's a starting point of reasoning. So the idea of it is a starting point. It's a fact or a premise or something that's self-evident that we start with, and we want to see where it goes. We want to see what we can deduce from these axioms. Okay, and this really goes into the idea that in general in this class, in this analysis class, oops. Is that we're sort of tearing down knowledge. We're starting from scratch. Okay, so we're starting from scratch here. And what we're going to do here is start with these axioms. So let's go to another page here. So we're going to talk about the natural numbers starting with these self-evident facts. And so there's 5, so the naturals. The naturals, which we're going to call this double-barred n, and it's a set of things. So, in our head, if I have a little thought bubble here, in my head, of course, we have, it starts at 1, and there's this line, 2, 3, and these numbers are all ordered on a line. And it goes on forever. But let's really cross that out. We don't know that yet. We want to actually start with what creates this thing that we're so familiar with. Are there a logical foundation that creates this and only that, that we can actually deduce this structure from a set of axioms? So n is a set of things and relationships. So let's start with the first one. We're going to call it n1. So there's actually so before I actually do that, so let's go into the axioms. And there's actually 5. Okay, so let's talk about the 5 axioms. The first one, n1. The n1, this one's going to seem a bit cryptic at first, and it's just basically there exists an object called 1. And I put that in quotes, and it's an element of this set of natural numbers. Okay, we don't know what properties 1 has, but we're just going to say that there's this special object. All right, let's go to the next one. N2. Okay, and it says now, and N2 is a little bit more something that's identifiable. For all elements N that are members of the naturals, all right. Again, it's a set. So there's these elements N of the naturals, and they don't have any properties that we know of yet, but we do know this. There exists a successor object which we'll call Sn, that's also an element of the naturals. All right, and you can think of it this way, is that N and Sn are a pair. And Sn is called it's called the next object in the set. Okay, so the idea that this notion of a next is very important, of course, for the natural numbers. Okay, so what do we mean by next? What really Sn is a function. Connecting object, connecting objects. In the natural numbers. Okay, so that's a very important idea. The idea that there's a next, and of course, when we think of the number line, we know that the next number in the sequence is 2, and 3, and 4. We haven't had this all fully sussed out yet, but the idea is that the idea of a next is very important for the naturals. N3, all right, and this is very we know that with the naturals there's always a next, but there is also a starting point. And so we say 1, the special number, the special element of the naturals, is not the successor to any other object in the naturals. Okay. All right, and what that means is, we can write it down as that Sn is not equal to 1 for all elements of the naturals. Okay. All right, so that basically means 1 is the starting point for the naturals. There's nothing before 1. Okay, so that's good. Sorry, I had to resize things there a bit. Okay, so now N4. N4 is that if we have an A and a B, 2 elements in the naturals, so consider it. So if we have two elements of the naturals, if SA is equal to SB, then it implies that A is equal to B. That is, if 2 elements have the same successor, then the 2 elements are equal. Okay, and that seems pretty straightforward. Again, because we have you probably have a picture of the number line in your head. You know that yes, if the successor to 4 is 5, and then you also found another number that has a successor that's also 5, you can assume that it must have been 4 for each case. Okay, so 5, and this one's probably the most cryptic one, and we're going to write it down here. And this if we have a subset, a subset A, and it could of the naturals with the properties one that 1 is an element of A, and 2 that if A is an element of capital A, then the successor is also an element of A. I.e., basically, this is a closure under succession. Okay, closure under succession. Then it implies then that A is actually equal to all the natural numbers. Okay, so these axioms, you're really going, okay, great. These all seem fairly straightforward in terms of how they sketch, in terms of how they square with what we understand the naturals to be. So, you know, so the question then is, how do I know and 1 through 5 are all necessary? Okay, and how do I know that these 5 axioms in and of themselves define what we think of as the natural numbers and not anything else? If I take away one of the axioms, will it open the door to things that are decidedly not going to be like the naturals that we understand them to be? And so, of course, the answer to that question is quite simple. Try taking away axioms and see what results. And that's basically what we're going to do with the rest of this video, is just try breaking the natural numbers by taking away axioms, by knocking out axioms, if you will, and then see what results from that. Okay, so let's try that. Okay, so so let's go back to these ones here. So we see that n1 is there is this object called 1. So with n1 itself, it's hard to knock that one out because it really doesn't say much about what 1 does. Really, it's connected to n3. n tells you more about what 1 is. So let's try again. Let's talk about how we can knock out some of these axioms. So really what we're going to do is try knocking out both n1 and n3 together. We'll try that first, and then see what results. Okay, so let's try doing that. Okay, so let's try removing n1 and n3 together. All right, and that means that 1 can be the successor to some other in the set. Okay, you know, what kind of things result? Well, I can think of one example And this is again an example of something that if you take away, or if you actually can enable one to be a successor of something, is you can really make what I would call a clock. So a clock, of course, is a means of counting or keeping track of something periodically, where we have, of course, 12 up there, and then we have 1, 2, 3, 4, 5, 6. Put the 3 over there. 7, 8, 9, 10, and there's an 11. And then after 11, of course, you go back to 12 again. And when you go to 12, of course, you can go to 1. So what we're going to say is we allow S12 to equal 1, right? And then, of course, S1 is going to equal 2, S2 is equal 3, and so on all the way till S11 equals 12. And so what we have, of course, here is a ring. I should say a loop. All right, and so clearly this type of system, this is of course this works perfectly fine. So I should say this is an allowable system. It's an allowable system of this set, that for succession to occur in some sort of periodic loop, like so. And that's because we've allowed now 12 to be linked to 1. So we obviously know in the natural numbers that can't happen. The next number after 12 is not 1, but we've removed that axiom, and that now can be allowed. And so we can get all sorts of examples, like with a clock, where that can happen. So now let's go study what happens if I take away a different axiom. So the question then is that can I take away another axiom? And the axioms I want to focus on now are, let's take away, what about N4 and N4. Now let's talk about N4, yeah. Let's take that one away. All right, what was N4 again? N4 was that if A and B have SA being equal to SB, i.e. the succession, then it would imply then that that A is equal to B. So now we're going to say that this is not always true. And that is removing the axiom. So what is that? What kind of system? Can we come up with an example of a system where this is not always true? And of course we could come up with a way of doing it. So if I go, again, I keep accidentally resizing my board, and I'm sorry about that. We can keep doing this now. We can try a system like this. I'm going to say we're going to take A, B, C. I'm going to put subscripts on these, A1, B1, and C1. Now I'm going to take A2, B2, and C2, okay? And I'm going to connect them. So I'm going to say the successor to A2 is B2, and I'm going to say the successor of B2 is C2. And then same here. The succession works like that. But then the successors here now, C1 and C2, both success onto what I'll just call D. And after that, we can say that's E, F, G, and so on forever. All right? And so this system now, we see that S of C1 is equal to D, and S of C2 is equal to D. All right, so what we see here is this structure is sort of like a tree. Okay, it doesn't look like a line. It's not a number line. In any traditional sense, but more like some sort of line or some sort of a tree-like structure. And that, of course, can happen if you don't have the axiom of N4, if you allow two elements to have the same successor. Okay, so clearly in some systems of mathematics, this sort of structure might be a very useful way to model things, but it's not the natural numbers by any stretch of the imagination. So now we see why N4 will be valuable. Okay, what about N2? Removing N2, what it does is it removes notion of succession, i.e., we have no idea of what Sn means. And of course, without that, we wouldn't have this notion of next. So basically, there's no next that we can talk about. And of course, that wouldn't bear any relation. All we're left with then is that n is some set. Okay, it doesn't have any properties other than it's just some set. So clearly that bears, it's just a bag of objects, right? Here's my bag. There's a 1, there's a 2, a 3, and a 4, and a 5, and a 6. And they have no relationship. They're not paired in any way. So of course N2 is sort of a foundational axiom. It's something we have to just accept, that there's this notion of next. All right, so what about then N5? N5 is very special. It's called the inductive axiom. It's very important that we have this axiom. I'm going to write down what that axiom is again. Of course, if A is some subset of the natural numbers, this set, and ampersand, 1 is an element of A, and that if A is an element of A, then SA is also an element of A, then it implies that the set that we're discussing, A, is the naturals. Okay, so this one's probably the most confusing as to what it's saying, and basically the idea is how do we knock out this axiom? Okay, let's suppose now. Suppose N5 is not true. Can I find a system that this isn't true? Okay, that N5 does not hold. And what I mean by system is a system of succession. A system of succession. Okay, and so what we're going to do now is say, let's suppose that S1 is actually equal to 3. Okay, so the next object after 1 is 3. We'll say that S2 is going to be 4, and S3 is going to be 5. Right, and this again is a different sort of pairing. What we're defining to be the next number is now a little different than what we're used to. Okay, and that S4 will be equal to 6. All right. Of course, we don't have any sense of the order of numbers. We're simply saying that the way that we're defining the next is not going to be in sequence like this. All right. So what we're doing then is saying that succession. We're saying is then I can start here. I can go 1 to 3 to 5 to 7 to 9 and so on forever. Basically, the odds succeed each other. Okay, and the same thing with the evens. 2 goes to 4, 4 goes to 6, and so on and so forth like that. All right, so here clearly, now let's just look at that. Okay, I'm going to say now, I'm going to let A equal the subset 1, 2, sorry, it's going to be equal to 1, 3, 5, 7, so on and so forth, all the odds. And of course, we're going to have this as our succession rule. And this is sort of a leapfrogging. A leapfrog succession. Okay, a leapfrog succession where you're skipping over one of the numbers to get to the next one in our more traditional definition of the naturals. Okay, and clearly 1 is contained in A, and it's closed under succession. But better write that down. But A is not equal to all of the naturals. We've missed all of the even numbers. So clearly, with this version of succession, the idea of a leapfrogging style succession, we don't get all the numbers. All right, we only get some of them. And so clearly, this violates our axiom N5. So this type of succession doesn't work. We need to find some better type of succession. We need so that tells us a lot about what succession means. So what we need so N5, we conclude that N5 requires that succession will start at 1 and will reach every number. Every object in the natural numbers, okay, without missing any. All right, so this is why they call it the inductive axiom. Because induction involves the idea of once you know it for the first one, and then if we can make sure that for every object in our set we can verify it's also true for the next one, we're not going to miss any, and we've covered everything. And that's why we call it the inductive axiom, because we won't miss any objects in this set. All right, so succession has to be of a very specific form, that we can't just choose any means of succession within the set, only a very special type of succession. So now, N1 through 5 creates precisely the natural number line. It starts with 1, and it goes on forever, from 2 to 3 to 4 to 5, and so on and so forth. We can't have, so there's no branches. There's no branches. Oops. There's no branches. That's, and it starts at 1. And we get to everywhere. We go through. There's no branches and no loops. starts at 1 and goes through everything. And I think of the axioms that we studied there, the axioms essentially guarantee that these sorts of properties hold for the natural numbers. And of course that gives us our very special understanding of the structure of the naturals as a line with a starting point, and it goes through in some successive sequence. Alright, so I hope that gets you a very clear picture of how axioms work to create something, and how we try to find out, or we distill this thing that we're very familiar with from when we were children, and it really distills it down to its logical, most fundamental components that must be true in order for the thing that we know, this natural number system, to be what it is. All right, so thank you very much.